Chapter 1, Section 7, more about derivatives. We've talked about this plenty of times now. Notation is very important. We want to make sure we are writing what we mean to write. So recall these notations. Please, please, please take note. If you're working with prime or you want to use the ddx notation, it is also important that we understand what it's saying and how to write them. Now, in this lecture, we're going to talk about taking the second derivative. So that is actually what those are the notation for. Okay, so just keep in mind too, variables don't always have to be x and y. If our function is f of t, then we have t squared. We would indicate the first derivative as the following. All right, so now we have the derivative with respect to t. So f prime of t equals 2t, or d over dt of t squared equals 2t, or if the function's named y, we say dy over dt equals 2t. And again, take a look below at those graphs. Everything that had an x now just has a t, but the slope, the points, they are all the same idea, but now just with respect to the variable t. All right, so we can use the same rules of derivatives to make the second, third, fourth derivative, and so forth. So over on that left side, if we had 5 x to the fifth, the first derivative would be the power rule, 5x to the fourth. The second derivative would be the power rule to the first derivative. So that's where we get 20x to the third, and so on. This right here is just the note to note that after the third derivative, we really don't write the little, we don't write f prime, 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 like 4 times. We don't just keep writing that. It becomes redundant. So you'll see those little numbers up where those little dots would be. So 4, 5, and 6 all mean the same thing, but it's just a little redundant and silly to keep writing those symbols. So keep in mind though, if we're using d dt or d dx notation, if we want the second derivative, it's d squared dx squared. And then the same thing with the third, and then also keep in mind if we're using it dy dx notation, that's what it would look like as well. Okay, so when evaluating a derivative at a specific value of x, if we had x equals a, we get a number, f prime of a, that gives us the slope of the curve at that point. So another way of writing this, if we are using dy dx notation, is basically, you see one bar and then at the bottom x equals a. So that's when we would take a and evaluate the function for a. All right, so let's look through these 2 examples. Maybe this will make a little bit of sense. So I'm going to switch to f prime notation just because I can do that. But the first thing I want to do is just state that f of, all right, so f of x is going to equal 3x squared plus 2x. And if you don't want to switch to f prime notation, then you can just say x equals, and then just make sure you plug in 2 at the end. So f prime of x is going to equal 6x plus 2. So then, now I just have to evaluate that derivative, that first derivative, for 2. So 6 times 2 is 12, plus 2 gives me 14. So we've seen problems like this before, but it was in this notation, this prime notation, but now it's just in the ddx notation. So again, kind of your preference. All right, so in your notes you have this is a 6, so I'm going to fix that. All right, so for this bottom one, the first thing I want to do is, I noticed that we have a radical. And again, when we have a radical, the first thing we want is a rational exponent. So I'm going to say, okay, well, I want to take the derivative with respect to x, but I'm going to rewrite it as 2x plus 6 to the 1/2. And then I'm going to evaluate that at x equals -1. Okay, so that makes me feel better. So now I can say, okay, f prime of x, I'm going to take that derivative, equals. So I'm going to need to do the chain rule because we have the inside and we have an outside. So I'm going to bring down the 1/2. The inside stays the same. I subtract 1 from the exponent. And now I'm going to multiply the derivative of the inside, which is just 2. All right, so when we simplify this, something does cancel right now. We have 1/2 and we have 2. So the first simplification, so I'm going to rewrite it, and I'm going to say, okay, 2x plus 6 over -1/2. All right, so I'm going to evaluate this, which is why we always simplify, so I'm going to put it down on the bottom. Okay, so now it's in a better situation to plug in that 2, or no, we're plugging in -1, excuse me. So f prime of -1 equals 1 over 2 times -1 plus 6, and then that whole denominator to the 1/2. Which gives us 1 over 4 to the 1/2, and we know 1/2 means the root, so our answer is going to be 1/2. All right, so we've talked about the marginal concepts before when we had a little project to do at the beginning of the year. So just some reiteration, I'm just going to read from what you can see in front of you. If the function c of x is a cost function, then the marginal cost function is the derivative of that. The marginal cost of producing A units is the derivative with respect to A. Is approximately equal to this function right here. C of A plus 1 minus C of A. So what does that mean? Basically, that is the additional cost that is incurred when the production level is increased by 1 unit. Okay, so if we go from A to A plus 1, we just take the difference of that. That's all that means. So the marginal revenue and marginal profit, if R is the revenue generated from the production of X units of a certain commodity and P is the corresponding profit, then the marginal revenue function is the derivative of our revenue function. And the marginal profit function is the derivative of our profit function. Okay, so here's an example. It's from our textbook on page 122. Suppose the cost of producing X items is that function below, or is producing X items is C of X, and then you can read that. Dollars, and the daily production is 50 items. What is the extra cost of increasing the daily production from 50 to 51? All right, so I just want to find the difference. So I'm going to plug in 51 to the equation and subtract when I plug in 50. So 0.005 of 51 cubed minus 0.5 of 51 squared plus 28 times 51 plus 300. And I'm going to do the same thing, but now with 50. All right, so when I type this in my calculator, for C of 51, I get 1,090.755 minus 1,075, which is about $15, and let's just round up 76 cents. Okay, so that's just asking for the extra cost of increasing. So now if I'm asking for the marginal cost was defined as the cost function, but the first derivative of the cost function. So the first thing I want to do is identify, okay, well, what is the first derivative of the cost function? And that gives me 0.015 x to the second minus x plus 28. I just did the power rule. All right, so now I'm going to plug in 50 for x. And when I do that, I get $15.50. All right, more on this will come a little bit later, but now you have the basic idea. All right, the last part of this. All right, calculus and trig functions. So this is just the beginning. We are going to do a lot more with these, but I just kind of wanted you guys to get a little bit of a little exposed to some of these. So the first three are just definitions. Straight up, this is the derivative of the sine function. It is the cosine function. And the derivative of cosine is not just the sine function, but negative sine of x. And then the derivative of tangent is secant squared of x. All right, so we are going to do the next three problems. The chain rule applies to trig functions too, so keep that in mind. So the sine is the outside and the 3x is the inside. So I'm first going to do, okay, cosine, because that's the derivative of sine. Keep the inside the same, times the derivative of the inside. And I'm going to just rewrite that as 3 cosine of 3x. All right, so the next one, the derivative of cosine is negative sine. We keep the inside the same, times the derivative of the inside, which is 4x. And again, I'm going to rewrite it, negative 4x sine of 2x squared. And this last one is going to be the derivative of tangent, which is secant squared. And the inside is 3x squared plus x. That stays the same. Now we take the derivative of the inside. So we're going to multiply it by 6x plus 1. So it's important to recognize, though, that we are going to multiply 6x plus 1, and we are just taking the secant function of, or secant squared function of just that one piece. And the last thing to note is down here at the bottom. So just keep this in mind. Whenever we have cosine squared x, or a trig function squared, this means the whole thing is being squared. It does not mean cosine of x squared. That means something else, okay? That, or not something else, that is its own thing. That's saying take the cosine of x squared, but I don't want that. I want to square cosine with it. So you are always going to rewrite it like this right here, okay? That's the first thing you're going to do. So now we're going to think, now we're going to take the derivative of that. Okay, so if we take that double box up top, we're going to take the derivative of. So the outside is the power rule, so 2 times cosine x, right? Now it's to the 1 if I subtract 1, times the derivative of the inside. So the derivative of cosine is negative sine of x. Okay, so then just to simplify this, we're going to do negative 2 cosine x sine x. All right, so that just gives you a start of the trig functions, but the basics of what you need to know to start.